In this video, we are going to discuss a couple of examples of relative motion in case of accelerated straight line motion. Now, if you recall, if you have two objects A and B, and the velocity of A as observed from B, or what we call relative velocity of A with respect to B, is velocity of A minus velocity of B. Now, to involve acceleration is really only going one step further. If you differentiate this equation with respect to time, you get acceleration of A with respect to B, and that equals acceleration of A minus the acceleration of B after differentiating every quantity in this equation here. Now, once we are aware of this, and we are also aware of the concept of uniformly accelerated straight line motion, when we observe motion of A with respect to B, we assume that B is at rest, it is stationary, and the motion of A is being observed from B. Since B is at rest, the study of motion of A becomes that much easier, because sometimes we have to, for instance, calculate the distance between two objects after some time. We have to calculate the time in which two objects meet, etc. And if one of them is stationary and only one is moving, then it's that much easier to make these calculations. If instead both were moving, we have a somewhat more difficult job on our hands, because when two objects are moving together, it's difficult to keep track of their motions individually as well as collectively. So we'll be using relative motion concept as a tool for solving a couple of problems, and you will then start to understand how much easier problem solving becomes once we use the concepts of relative motion. So let's take up a fairly simple problem to start with. We'll be taking up an example of vertical straight line motion. Let's say this here is the ground, and from the ground we are throwing an object A in the vertically upward direction, and let's say it has a velocity u. Now, at a fairly large height from this point, let's say h, this is height h, and there's a point vertically above A, and from here we are dropping an object. So let's say this object which we are dropping from here, this object is B. The moment A is thrown upward with speed u, B is dropped. Now, since B is just dropped, its initial velocity is 0. Now we have to calculate the time after which they collide, the height at which they collide. These two things we have to work out. Now, what we can do is we can study their motions separately and work out the time after which they collide, and then calculate the height at which they collide. But the problem becomes that much simpler if we study their relative motion. The initial velocity of B is 0, and the initial velocity of A is u. We're taking upward direction as positive and downward as negative. Acceleration of B is minus g, the acceleration due to gravity, minus because it's in downward direction, which is negative direction. Acceleration of A is also minus g. Now, looking at accelerations, what is the acceleration of B with respect to A? Acceleration of B with respect to A is acceleration of B minus the acceleration of A. And this gives us minus G minus minus G, which is 0. So, if we are looking at the motion of B from A, imagine that you're sitting on A and looking at B, then B appears to be moving with 0 acceleration. Also, what about the velocities? What is the initial velocity of B with respect to A? This will be initial velocity of B minus the initial velocity of A, and that is 0 minus U, and that's minus U. Now remember, we are studying relative motion of B with respect to A, and when we study relative motion of B with respect to A, we are assuming that A is at rest. So A now is at rest. This is A. It is at rest. Initially, B is at a height h above A. This is B. It is at a height h above A, and it is moving in the downward direction. Now, A is at rest and we are studying relative motion of B with respect to A. Initial velocity of B with respect to A is minus U. Minus means downward. And the acceleration of B with respect to A is 0. So if you are sitting on A, assuming yourself to be at rest, and looking at B, B appears to approach you with a velocity minus U. Now the first thing we were interested in calculating was the time after which they collide. Now if A is at rest and B is moving with a constant velocity of magnitude minus U, the displacement of B with respect to A for the collision is minus h. A is at rest, B moves with velocity minus U, has to undergo a displacement minus h to finally collide with A. So the time after which this collision happens is simply minus h by minus U, displacement divided by the constant velocity, and so you have h by U. Very easily calculated, the time after which collision takes place. The second thing we are interested in calculating here is the height at which this collision happens. Now, we've calculated the time after which collision is taking place. Now what we can do is, motion of B is very easy to understand. It starts with 0 velocity and moves with an acceleration g, and therefore B will move downward by a distance ut, t being u h by u, ut plus half a t square. Now t is h by u again, so h square by u square. So this height by which B drops in this amount of time, it comes out to be this distance by which B drops is minus gh square by 2u square. Now the minus sign actually tells you that this is a downward displacement, that's why it's a negative displacement, and therefore the collision has taken place at this height, which will now be equal to h minus this quantity. The minus sign is again, if you remove the minus sign, you have this magnitude, and from this h height you remove that magnitude, you end up with h minus gh square by 2u square. This is the height at which the collision between A and B takes place. So you might notice that relative motion ideas made the problem that much easier to solve. We will look at one more example where you will understand that the ideas of relative motion, the concepts of relative motion make problem solving that much easier. So one more example on this, and we are pretty much done with this video. Now in the second problem that we are discussing, think of two objects A and B. This is A over here. This is B. The distance between A and B is 40 meter. Initially, A is moving towards B with a speed of 10 meter per second square, 10 meter per second, I'm so sorry, 10 meter per second. At the same time, at the same instant, B starts moving in the same direction with an acceleration of 2 meter per second square, and since I'm saying it starts moving, its velocity initially is 0. So acceleration of B is 2 meter per second square, initial velocity of B is 0. Initially velocity of A is 10 meter per second, and it has a 0 acceleration. The question is that we have to find the minimum distance between these two particles A and B. Now it is fairly obvious that A is initially moving much faster, and since A is moving that much faster than B, it is coming closer to B. But what happens with B here is that it is speeding up, and as it speeds away, it eventually starts moving faster than A. And since B starts moving faster than A eventually, it runs away, and the distance between them, obviously starts to increase. So initially, because A is moving faster than B, the distance between them decreases, and then because B is speeding up, the distance eventually starts to increase. So the question is that we have to calculate the minimum distance between A and B in this problem. Now if you look at the motions individually, the problem may be a little more complex because you have to look at two different motions taking place at the same time. But if we convert this problem into a problem of relative motion, let's say we look at motion of A with respect to B, then B is at rest in the study of relative motion. B is at rest and only A is moving. And the problem therefore becomes that much simpler to handle. So, initial velocity of A with respect to B, initial velocity of A with respect to B will be initial velocity of A minus the initial velocity of B, which is plus 10 meter per second. Now we are taking the right direction to be positive x and the left to be negative x in this motion here. Now what is acceleration of A with respect to B? Acceleration of A is 0 minus the acceleration of B, and the acceleration of B is 2 meter per second square, so we have minus 2 meter per second square. So let's convert this now to a problem of relative motion, and in this B is at rest this is B, it is at rest. Initially A is 40 meter away and is moving towards B, and the velocity with which it is moving towards B is known to us already. It is known to be how much? Plus 10 meter per second, and the acceleration is known to be minus 2 meter per second square. So we have a case here where the initial velocity and the acceleration of object A are opposite in direction, as indicated by the opposite signs. Now this kind of a motion invariably involves a turning point. If you recall the previous couple of videos, then you will remember the idea of turning point. The motion of A involves a turning point. B is at rest, A moves towards B, but its speed is reducing. Before the turning point, it's a speeding down motion where speed reduces. So the speed of A is reducing. A comes with reducing speed. It stops here, and at this turning point it has stopped, and then it reverses direction and moves away. So the path that A is following will be somewhat like this. A moves towards B, stops, and then takes a U-turn and runs away. Now when it stops over here, its distance from B is the minimum distance that we are looking at. So A is moving towards B, it stops here momentarily, and because it has an acceleration minus 2 meter per second square, it starts moving in the direction of that acceleration after stopping here at what is called its turning point. Now at this turning point here, the velocity has to become 0. So the velocity at this turning point is 0. What we'll be calculating is this distance up to which its velocity becomes 0. So let's say this distance is s. The final velocity here is 0, initial velocity is 10, and the acceleration is minus 2 meter per second square. So v square minus u square, v square minus this u square, that is 10, equals 2a times this s. See, when we are using ideas of relative motion, all those equations that we have studied, all these ideas that we have studied so far, they all remain applicable. And we now have minus 100 equals 2a. Acceleration of A with respect to B was minus 2, and we now calculate s, the displacement over here. This displacement s now comes out to be 25 plus 25 meter. So that means this displacement s is in the positive direction. So A travels 25 meter and then stops and reverses direction and moves further away. So after moving 25 meter, it stops, reverses, moves away, and at this instant when it stops, it is closest to B. Now the total distance was initially 40 meter and it has traveled 25 meter and then reversed. The remaining distance now is the shortest distance between A and B, and this shortest distance therefore will be 40 minus 25, and that's 15 meter. So again, a very simple and yet very interesting application of the concept of relative motion. Now, we are pretty much at the end of our topic of straight line motion. In our next video, which for the moment will be the last for the current session, will be the last video on straight line motion. In that video, we'll be discussing some miscellaneous kind of problems. For instance, we haven't really discussed any problems involving velocity position graph, acceleration position graph, also some random kind of problems, the kind of which we have not really discussed so far. So the next video will be about miscellaneous problems on straight line motion. I come to the end of this video on relative motion. Thank you very much for watching. Please like, share and subscribe. Keeps the channel growing, keeps me encouraged to try and do better work in the time to come.